Now children, now we'll be discussing about the extraction of one of the very important metal which is there, that is called aluminium. So we'll be discussing that from its ore, that are cryolite or bauxite, whatever is there, corundum is also the one, how is it being extracted. Now if you see what we discussed in the previous session which was there, that what was the first step involved? The first step was we had to do what? The first of all we'll be discussing what were the ores. Okay, so ores of this are bauxite. So this is the main ore children which is there, and bauxite is nothing but your aluminium oxide, but then it's hydrated. So this is my most important ore. Then I also have cryolite, and cryolite goes by the formula Na3Al(F6), and my next another important ore will be corundum. So that is also my Al2O3. So the difference between bauxite and corundum is that children, that bauxite is hydrated aluminium oxide and this is normal aluminium oxide which is there. So aluminium, you all must be knowing, it is the most abundant metal in the earth crust children. Means almost, if you see on the entire earth crust, if you see 7.4% by mass it is present. So it is understood to be the most abundant metal which is there. And then we have in the second we have iron which is present how much? 4.7%. Now aluminium does not occur in free state since it is a reactive metal. Okay, so this is the reason why it is not occurring in a free state. It is being found in the form of bauxite, cryolite or corundum. So this is the thing, and from these ores we will be extracting the metal. Now we will be saying that what are the steps involved in the process of extraction children. The first step, if you remember, that we discussed was dressing the ore, wherein what do we do? In dressing the ore we just remove the gangue particles or the matrix particles which are there. The external impurities which are there, they will be cleaned up or they will be removed. Now the first step which is there in dressing the ore is conversion of impure bauxite to sodium aluminate children. Okay, so what is happening? Step by step we are doing the process. So the first step is conversion of bauxite to sodium aluminate, which is written as what children? NaAlO2. So the reaction which goes on is, you can see on the right side of the sheet, it is bauxite is my Al2O3 dot 2H2O plus it reacts with sodium hydroxide, and the temperature which is there is usually taken as 150 to 200 degrees Celsius, and then this converts to sodium aluminate, that is 2NaLO2, and then I have water. Okay, so this is what is happening. I am just adding sodium hydroxide with bauxite and then it is giving me sodium aluminate. Now we will be discussing that what is the functions or what are the functions of this sodium hydroxide. Now this sodium hydroxide which is there is the first step, the impurities which is there. So this happens to be the first step of the process, dressing the ore, and in this the bauxite is reacted with concentrated solution of NaOH and then under pressure for 2 hours. Okay, so this reaction, this goes on for 2 hours. The impurities that are present in bauxite, which is mainly what children, this is Fe2O3, that is our ferric oxide, and SiO2. What is SiO2 children? It's basically sand. They remain unaffected with concentrated NaOH since the impurities are not amphoteric. Now bauxite is amphoteric, so it reacts with base forming salt and water, hence impurities are separated out. So this is the reason why we are adding NaOH. So once we are adding this NaOH or caustic alkali which is there, what will happen children? The Fe2O3 and the sand particles which are there, they are unaffected by the NaOH which is there. Okay, so what are my gangue particles here? If I want to write down children, the gangue particles in this will be Fe2O3 and SiO2. So these are not getting affected because the impurities which are there, they are not amphoteric. But then our bauxite is amphoteric in nature. It reacts with base and then it's for NaAlO2, and then what happens, this impurities Fe2O3 and SiO2, they are separated out. So this is what we are doing in dressing the ore. Now we are getting what? We are getting sodium aluminate. Now what I will do, I will try to convert sodium aluminate to aluminium hydroxide which is there. So what is the reaction that is involved in that? What I will be doing, this sodium aluminate, this I will be diluting it by adding water. I'll be heating to the temperature 50 to 60 degrees Celsius, and then I'll be getting what? I'll be getting sodium hydroxide plus this is aluminium hydroxide. So this is what I am getting. And then why did we do this, children? Because at the end I want the oxide form of this particular ore which is there. So here I am having aluminate form. From aluminate I am going to hydroxide. So here what is happening? What did I do? So you can consider this as step 2, wherein aluminate is getting converted to hydroxide, and then there is a process which is termed that was seeding, children. Okay, this particular reaction, this will be called as seeding reaction. So if an exam you are being asked what is seeding, then this is not a reaction, children, this is a process. So what will be your answer? When sodium aluminate is diluted, then it gives aluminium hydroxide. So this particular process is called seeding. Alright, and then how do we remove this AlOH thrice from this particular solution, children? By agitation. Okay, when we agitate this, what happens, children? This AlOH thrice, this is insoluble and hence it gets separated out. Okay, so if it is insoluble, it's sure that you can just remove it maybe by filtration or any other process which is there, and then this is being dried and we are able to take out AlOH thrice. Now in the third step, what we do, children, this AlOH thrice, this is being heated again to give pure alumina, because this is still in hydroxide form. So I'll be heating this to 1100 degrees Celsius, and then this gives me aluminium oxide plus water in the vaporous form, and this is my alumina, and then my final dressing step stops. So this can be considered as step 3. Okay, then precipitated. What is the step? What you can explain? How can you explain this, children? That the precipitated, whatever AlOH thrice it was there, that is being ignited, means heated to 1100 degrees Celsius to give me pure alumina. So this is what I am getting, the end product as a result of the concentration of ore. Okay, so this happens to be my first step, wherein what we did, children, in the first step, if you remember, I'll just explain you once again. In the first step, what I formed in the first step, I was getting the sodium aluminate. If you see here, we'll be discussing this. See, children, so in the first step I got sodium aluminate. Then what happened in the second step, this sodium aluminate, this was being converted to sodium hydroxide, and in the third step this aluminium hydroxide, and this aluminium hydroxide was then converted to Al2O3, and then my concentration process is over. Okay, and then there is a alternative process, children, how you can concentrate or dress the ore. This is called Hall's process. So basically in this chapter, what is important, children, you should know the names of the various processes which are there, and that is the thing. So what is Hall's process, children? Here what I will be doing, see, first I will be converting, this is the reaction that has been given, this is the bauxite. Okay, this I will be treating with sodium carbonate, and this will give me what? This will give me sodium aluminate plus water plus CO2. So this is my first step. In the second step, this sodium aluminate which I got, this NaAlO2, this I'll be passing what, children? See, the 3H2O. Okay, and then I'll be adding carbon dioxide. So this will be giving me what? Na2CO3 plus AlOH thrice, which is there, that is being precipitated, children. Okay, so once I get this precipitation of AlOH thrice, then again I'll be just heating the process and then I'll be getting the pure alumina. So this is the alternate method, that is called by Hall's process, wherein what we are doing, children, instead of just reacting it with sodium hydroxide or the caustic soda as we did in the previous step, here we are reacting with sodium carbonate and then I am getting sodium aluminate. This is being further reacted with carbon dioxide and water to give me Na2CO3 and precipitated form of aluminium hydroxide, which again will be heated, the last step being the same, to pure alumina. So what is my end product, children? If you see, my end product of the dressing of ore or the concentration of ore which is there is Al2O3. Now this Al2O3 will be carried forward for the next steps. Now the second step is what, children? If you remember, in the second step we did what? See, I'll tell you. In step 2 we just conversion of the whatever or the concentration was there of ore to oxide form, if you remember. Now why is this step skipped in this reaction, children? Because whatever the end product we got in the process of dressing, it was already in oxide form. So once it was in oxide form, it was not needed for me to carry out any roasting or calcination which is there so that it can be converted into oxide form, because my already end product was in oxide form. So we directly go to step 3, children, that was called what? Reduction of metallic oxide. So if you remember what we studied yesterday, children, that for aluminium the process which is there is electrolytic reduction, because we have other two, we can use reducing agents or we can go for the thermal decomposition as well, but for aluminium it was electrolytic reduction. Now what we do here, children, this is an important thing, and this is called what? The entire process is called, this is an important term, and this is what you can be asked in the exam. This is called Heralds, not Halls, children, this is Heralds process. Okay, so this name you have to remember, and this is very important, children, that the electrolytic reduction undergoes the process that is called Herald. Now what happens here? First, there is an electrolyte, children. If you remember what is electrolyte, so in electrolytic reduction we have a tank like this, wherein we will be putting an electrolyte, that is the molten state, wherein we will be dipping what, children? The anode and the cathode, that are the electrodes. Now what happens, children? In the electrolyte, what I'll be taking, I'll just tell you. So here we'll be taking Al2O3, okay, and then I'll be taking Na3Al(F6), okay, that is my cryolite, and fluorspar. Now what is the ratio? The ratio will be 1:3:1. So all these steps you have to remember, children. In this ratio I'll be taking the alumina which is there, which I got from the process of dressing the ore, and then I'll be adding to it cryolite, and then I'll be adding fluorspar as well, and this will be acting as my electrolyte. Now we'll be moving to the cell part which is there. Then what happens in the cell, children? If I want to just show you here, you know that for electrolysis I need to have an anode, I need to have an cathode. Okay, so what will be cathode here, children? Cathode will be a lining of the cell which is there. Okay, this is the lining of the cell, and this will be made of carbon. So I'll just write down here this is my carbon lining. Okay, and this only acts as cathode. There is no separate electrode for that. And when we talk about anode, there are thick carbon rods. So not one, will be having many carbon rods like this, children. So this will be acting as my anode. Okay, and then they are attached to the copper glands dipping to fuse. So what else is there in this, children? This is my electrolyte. Okay, the red portion, because we have filled this with the electrolyte which is there. So what is there? This is my cathode, children. This is my cathode lining. These particulars are my, if you can just see, this rods which we have inserted here, these are my anode, and these anodes are made up of what, children? These are thick carbon rods. So this will act as my anode, and then of course I have my electrolyte which is there. Now what is the temperature that I will be providing, children? Temperature that is there is 950 degrees Celsius. And then further what? This is how much current is being applied. The current that is being applied is 100 amperes, and that too at what volts, children? 6 to 7 volts. So this is my complete setup of the electrolytic mixture which is there. So this is an important one, children. And then how does reaction proceed in this, children, if we want to discuss? The first reaction is, see, the cryolite which is there, if you can see here, this is being reduced to Al3+. So this is the diffusion part that is going on, children. This is the breaking of the ions. Now fluorspar which is there, that is being reduced to Ca2+ and the F1-. Okay, and then when we talk about alumina is being broken down to 2Al3+ plus 3O2-. So these are the free ions which are being, like, they are floating in the electrolyte which is there after the reactions which are there. Now what is the particular reaction which goes on the cathode, children? This is really very important for you to understand, and you need to remember this as well. So in an electrolysis process, this is what is important, that what are the reaction that goes on cathode and anode. So in cathode what is happening, children? The Al3+ ions which I got from the alumina, this is reacting with 6 electrons, and then this is giving me 2Al. And then why 6 electrons, children? Because it is short of 3 electrons. So 3 electrons for 1 aluminium, and 2 aluminium I will be needing 6 electrons. So this is giving me 2Al. Now if I move to the anode part, what is the reaction that is taking there, children? The oxygen ions which are there, anions. Okay, so these are losing 6 electrons, and these are giving me what? 3 oxygen, or then this will be written as 3O2. Okay, so here aluminium is gaining electrons, and oxygen, an ion which is there, this is losing electron. The Al3+ ions which are produced, children, they are discharged in preference to Na1+ and Ca2+ ions due to the lower position in electrochemical series. So we just discussed the electrochemical series, children, and we know that Na and Ca which are there, they are high in position as compared to Al3+. So what will be happening? The Al3+, they will be easily discharged. Okay, and then what is the product form, children? Easily you can see that what is being formed at the cathode. At cathode, Al is being formed, and what is being formed at the anode? The anode which is being formed as Ca. At anode, oxygen gas is being formed, and of course we are having CO and CO2 as well. Okay, so this is the entire reaction all about. We can just discuss this shortly with the help of this diagram which is there, children. So this is what we discussed in the figure which was there, children. This carbon lining which is there, the outside carbon lining, this is acting as my cathode. Then these particular rods which are there, these acts as anode, and the electrolyte which is there is a mixture of alumina, and then we have sodium aluminate and fluorspar. So all of them, they are ores of aluminium, and then we'll be carrying out the electrolytic reaction, and then what I'll be getting at cathode pure aluminium, and at anode the oxygen is being released. So this is what is happening. So this process is called, children, Hall-Heralds process. Now if we go to the other thing, children, now in the electrolytic reduction by Hall-Heralds process, what is happening? The fused alumina is electrolytically reduced to aluminium. We discussed this already. Okay, now Al2O3 is a highly stable oxide and aluminium has a strong affinity for oxygen. Hence Al2O3 can be reduced to Al electrolytically only and not by reducing agents. Okay, so their children, they are saying what? That why is it that Al2O3 which is there, why cannot we reduce this with the help of thermal decomposition or with the help of the reducing agents which is there? Because it is having very high affinity with oxygen. So this is also a question that you can be asked, children, that why do we have to reduce aluminium only electrolytically? Now what is the second point which is there, children? What are the difficulties that we face during the electrolytic reduction of aluminium? So the difficulties which are there, children, is the fused alumina is a almost non-electrolyte and has a melting point of around 20-50 degrees Celsius. Okay, now fused alumina that we use, children, as an electrolyte, if you remember, in this tank what I used as electrolyte, I had Al2O3, I had sodium aluminate which was there, AlO2, and then I had cryolite as well, that was CaF2. Okay, and in this what is happening, children, the alumina part which is there, it is almost a non-electrolyte. What is non-electrolyte, children? The thing which cannot be act as electrolyte. Why? Because its melting point is very high. So this alumina is having very high melting point. So if we want to just melt this, only the melted form can be used as an electrolyte. So we'll have to heat it at across 20-50 degrees Celsius. Now what happens at such high temperature? A large amount of electrical energy is required. Of course, if I want to increase the temperature of the cell by 20-50 degrees Celsius, children, the amount of energy that is being required is very high. And what is the second point, children? That the liberated aluminium which is there, and it has got only melting point of only 660, may also tend to volatilize out and get wasted. Hence the fusion temperature of the electrolytic mixture which is there has to be lowered. So what is this, children? That once we are getting what? Once I am getting aluminium in the porous form at my cathode, now what they are saying, children, that it has got melting point of only 660 degrees Celsius. Now what happens if I am providing the temperature of how much? To 20-50 degrees Celsius, then what will happen? This can tend to volatilize, children. It can become a volatile compound and it can get wasted. Now if we want to remove this problem of wastage, what will I have to do? I'll have to lower the temperature of the entire electrolytic cell which is there, so that I can get maximum output of my aluminium. So these are the difficulties which are being faced. The main thing is that what, children? That my alumina which is there, the molten alumina that is having a fused alumina, is very high melting point. So I have to increase the temperature of the cell, which is again requiring me lot of electricity. And the second point is that the aluminium what I am getting out, this has a melting point of only 616 degrees Celsius. So we always have a, there is a chances that this will get volatile. So we'll have to reduce the temperature of the cell. Now what is the third point, children? The fused cryolite which is there and fluorspar are added to electrolytic mixture. So these are basically what are the important points which are there, which are being carried out in the process of the Hall-Heralds process. So these are what are being discussed, children. So fused cryolite, children, if you remember this, I just took, so this was, I took Al2O3 in the electrolyte, and then I had AlF6 and then fluorspar. Okay, so these are being added. So why are these being added, children? Cryolite in this mixture and fluorspar which is there. So if you remember, the ratio which I was having is, this is 1 part, this is 3 part, and this is 1 part. Then why are we adding a high amount of this, children? There is a reason. It just reduces the fusion point of the mixture. That is, the mixture is, see what is happening, children, what we studied, that this Al2O3, when it is individually being heated, it melts. Okay, so the ratio was how much, children? 1:3:1. Then why are we just adding this? This is my cryolite and fluorspar, children. This is to just reduce the fusion temperature or the fusion point which is there of the mixture. Now what is the fusion point, children? Fusion point will be the point at which all of three of them will be found in the molten form. So they will go for a melting, that is my molten form, and then only I can use that mixture as an electrolyte. So that is the reason we are adding these two, children, because addition of cryolite is going to, so earlier it was, what was the temperature at which this alumina was getting melted? This was 2050 degrees Celsius, and now on the addition of this cryolite, the fusion temperature, that is the melting point of this entire mixture, is getting reduced to 950 degrees Celsius. So this is the reason why we are adding cryolite at a high concentration which is there, in spite of the fact that it is having very low concentration of aluminium. Still we are adding, and then now you know the reason why. And then also what is happening, children, these two things, the cryolite and the fluorspar, they are helping me to increase the or enhance the mobility of the fused mixture. So what is happening, children? Basically, if this is my tank and this is my fused mixture, so what happens, the more the mobility of the electrons will be there, the more easier it will be for me to take out the process of electrolysis. So for the process of electrolysis, it is very much essential for me that there is an increase in mobility. So this is why these two are being added. This is the only reason. So what can the question be of type, children? The question that can be asked is, why are fused cryolite and fluorspar added to the electrolytic solution? So the first answer will be lowering the fusion point, and second will be enhancing the mobility of the fused mixture. Okay, and then the third point is also, it is also increasing the conductivity of the mixture, if you can see. Now what is conductivity, children? Of course, if the flow of electron is going to increase, then the conduction power is also going to increase. So this addition of these two is also going to increase my conductivity. So this is also one of the reason which is there, the third reason. And then since the pure alumina which is there, children, if you talk about alumina, which is the main ore of this aluminium, this is a very bad conductor. So if I want that this should conduct electricity, because ultimately electrolysis is all about conduction of electricity, so it is very important for me that alumina is, this particular mixture, not only alumina, this particular electrolyte which is there, it should conduct electricity. So addition of these two is helping me to conduct electricity as well. Now the compounds in the electrolytes are thus what? Al2O3 and Na3Al(F6). Now Charles Hall, who was there, Charles Hall is the scientist who just found out all these ways that how can we extract aluminium from Al2O3 very beneficially, and he just did all these steps, and then what happened, finally the extraction became simpler and cheaper, because initially what was happening, we were needed to heat up to 2050 degrees Celsius, which was practically very costly and as well as difficult. And then Al2O3 was a very bad conductor, so that also was a reason. So what happened, this particular scientist Hall, in 1886, he just discovered all these ways in which the taking out aluminium was now becoming easier and more economical for me. Alright, so we'll be moving to the fourth thing, children, that there is a layer of powdered coke which is sprinkled over the electrolytic solution. So suppose this is my electrolytic tank which is there, and then they are saying what, children, above this I'll be adding a layer of coke. Okay, so why am I adding the layer of coke, children? There are two reasons. The first reason is that the carbon electrodes which are there, okay, so it prevents the burning. So what happens, these are my carbon electrodes, children. Okay, so what is happening, since they are, if they are open, children, there are many chances that they will burn openly in air. So what will happen, it will just, by the time, as the time proceeds, this will start evaporating. If it is burning, then it is understood that more and more of it is getting ended up. So to reduce this process, what can I do? We will be adding the powdered coke. So it acts as a layer so that these carbon rods are not now open in air, and so it acts as a shield. Okay, and then what happens, it minimizes or prevents the heat loss by radiation. What happens, children, if suppose this mixture which is there, if this is completely open, okay, this mixture of electrolyte, if this is open, then what will happen, there will be a evaporation. Of course, if it is open, the temperature is very high, then the top layer will tend to evaporate. But then when we are adding powdered coke, then this will act as a shield again, and then the process of evaporation can be reduced. If not stopped, it can be reduced. So this is also a reason why we are adding powder coke. So all these questions, children, can be asked in 1 or 2 marks, so you need to study them very well. Now if we talk about the 5th point, children, the graphite or the carbon rods are continuously replaced during the electrolysis. Now what is here, children? These are my carbon rods which are there. Okay, I just bring them back. Okay, so what is the carbon rod, children? What is happening? These carbon rods, as the time proceeds, this will tend to evolve oxygen. Okay, then what is happening, when it is evolving oxygen, this oxygen is escaping in the air. Then what happens, as the time passes, this carbon anode is just getting oxidized to carbon monoxide, which is either burning or giving carbon dioxide, or it is escaping through the outlet. Okay, so this is what is happening. Upon oxidation, this carbon rod, this is being converted either to carbon monoxide, or further it is getting converted to carbon oxide. Okay, carbon dioxide. So this is getting continuously used up. Now what is happening, if it is getting used up, it is very important for me, children, to replace this. Okay, so if this process is a continuous one, I am continuously replacing this carbon anode which is there, so that the process does not stop. Okay, and why is the process stopping, children? Because the carbon anode, it is coming in contact with oxygen to form carbon monoxide, and which is further getting converted to carbon dioxide, and then these are escaping in the air. So like this, what will happen, entire carbon will get used up, and then we won't be left with any carbon. So we are replacing it at every regular interval. Then what is happening, that is therefore preferable to use a number of graphite electrodes as anode instead of a single electrode. So this is the reason, children, why we are here. If you see here, we are using large number of electrodes. In this electrolytic solution, you must have seen there are many number of electrodes which is acting as anode, and you now know the reason why. If the number of electrodes are more, it will be easier for me to, like, if the process of this change is happening, then if more numbers are there, then the carbon rods can be last for more time. So this is the reason why, and as the time elapses, what happens, we'll be replacing these rods. Okay, now the sub question 6, if you see, children, electrolytic reduction of alumina is a continuous process. So this also you have to remember, that pure alumina which is there at cathode is produced at the cathode, aluminium, and being heavier than the electrolyte is settling down. Okay, so this is what is happening. The pure aluminium which is there is settling down at bottom, and this is taken out continuously. Okay, and then it is periodically removed through the outlet. Now as the concentration of Al2O3 falls, the resistance of the bath increases, indicated by a glow on the control lamp, and this moment mole alumina is added. So what is happening, children? This process which is there, it tends to go on continuously. The moment I realize that my electrolyte is getting reduced, okay, there is a mechanism behind that. There is a machinery which will indicate you that the electrolyte is getting consumed. Then what I'll do, I will just add the electrolyte which is there, and then again what will happen, the aluminum is being formed. I am replacing the carbon anodes as well, and this way the process is continuous. Okay, and then at the end, whatever aluminum I am getting, children, that is almost 99.5% pure. Almost pure. So but then if we want to make it still pure to 99.9%, I'll be going for electrolytic refining which is there. Okay, electro refining, and there I'll be getting pure up to 99.9%, and that process will be considered or called as what? Hoops process. Okay, children, so we'll be now discussing what is Hoops process, and simultaneously we will be seeing that what is the fourth step in the extraction of aluminum which is there. So this is my fourth step, children, wherein what is happening? Electro refining of impure metal. Okay. So this is step 4, wherein we'll be discussing electro refining, children, and electro refining is carried out by the process which you know already, and then for aluminum this particular process is called Hoops process. Okay, and this is the final step of the extraction of aluminum after. So this is what is there. Now what happens in the Hoops process, children? I'll let you know. So this is my container which is there. Okay, I'll draw this properly. So I have a container like this. Again it is an electrolytic mixture. So this has been divided into 3 layers, children. Okay. Now in the first layer what I'll be having? In the first layer I'll be having pure aluminum. Okay, and what I'll be having in the second layer? Second layer will be a mixture of, this is an electrolyte, and it will be a mixture of number of things, children, that is BaF2. Okay, then I'll have ALF, CaF2, and then I'll have cryolite as well. Okay, so this is my thing, and in the third layer I'll be having impure aluminum. So this second layer which is there, children, this will act as a electrolyte. Okay, so this is acting as my electrolyte. The first layer which is there, children, okay, this is acting as my cathode. Okay, and then this particular, the last layer which is there, that is acting as my anode. Okay, then what happens? The lower layer is an impure aluminum that will be considered as the carbon lining which is there, impure aluminum, and at the bottom it is called, the bottom which is there is carbon lining. Now what are the electrolytic reactions which are taking place, children? From here, from this impure aluminum, what will happen? First there will be a movement of, see, at this place I'll tell you what is the reaction that is being carried out at this lower stage. This is called the cathode. Okay, so we'll see the reaction that is being there. So impure Al which is there, this is releasing 3 electrons and this is giving me Al3 plus ions. Now these Al3 plus ions, they will be moved towards the middle layer. Now from the middle layer what will happen? At the cathode which is there, this Al3 plus is going to combine with my 3 electrons to give me pure aluminum. So this is the process of electro refining which is there, children. Okay, so wherein I'll be having pure impure Al, and in the middle I'll be having electrolyte consisting of these 4 mixtures. Okay, and then as the reaction proceeds, we'll see what happens as cathode, we'll see what happens as anode, and then we are good to go. What is the end product that we are getting, children? We are getting a pure aluminium which is about 99.9% pure. So this is the way we are taking this process. So here this is the thing which you can see, children, and then the pure aluminium which is there is being easily extracted. Now we will be seeing the summary part of this, children. This entire process of taking out aluminium has been beautifully summarized in this table. So in the first thing which is there, children, from what did we discuss? The alumina, it is being reacted with sodium hydroxide to give me what happens in that process. I am getting sodium aluminate, and in between whatever the gangue particles or the external impurities which are there, they are getting reduced. So this particular process is called, children, what? It wasn't there when we discussed. So this process is called Bayer's process. Okay, wherein the very first step in the dressing, wherein what we did, we just bauxite which was there, we reacted it with sodium hydroxide. So it is the reaction which has been given, which we discussed already. Now in what happened after sodium aluminate, this what again heated up. It went for hydrolysis, not heated up, and then we got what? We got precipitated form of AlOH thrice, which was further heated to 1100 degrees Celsius, from where we got Al2O3, the alumina. Then the second process was wherein we convert the concentrated ore into the oxide form, but here already it was in oxide form, so we just skipped the second step. When we moved to the third step, there we underwent Hall-Heralds process. So what happened in Hall-Heralds process, children? This electrolytic reduction which was there, this just gave me what? These are the particular reactions which happened at the cathode and the anode, which we discussed. At cathode we were able to collect aluminium that was 99.5% pure, and then for the further pure form of aluminium we went for Hoops process of electro-refining, wherein at the end I was able to get the aluminium which was 99.9% pure. So this is the entire process of the taking out aluminium. So this is the way it is there.